And then if I go back to this, and we're done, we're recording. And Carmen will carve out this part. And you have their mics throughout the room, so you can sort of stand anywhere. All right, we're going to begin. This is the last of the CLOSC lectures. I don't remember if it was introduced what the CLOSC lectures are. Since 1966, this is endowed by the family of a former NYU graduate student, PhD student, Stanley CLOSC. So just remember that, graduate students, as you go out into the world. Every few years, as the spirit moves us, we invite somebody illustrious to give several lectures about their work. This year it's Sara Seager. Sara was a graduate student at Harvard and then went to the Institute for Advanced Study, went to Carnegie, the Carnegie Institute of Washington, the one in Washington, is that right? And is now a professor at MIT, and she's going to tell us about exoplanet atmospheres.
Thank you. Thanks everyone, especially those of you who came to all 3 talks. So I had to think about, after I've been here for a few days, what would be the best thing for me to talk about today, because I want to leave you with like knowledge in this field, appreciating that you probably don't get a lot of talks on exoplanets here. So I decided so it's a little different from what my title says, maybe not as technical as I set out to be, but I have something for everyone. So in this case, I wanted to start by telling you that something absolutely amazing in exoplanets happened in the last year of the last century, 1999. I'm not sure if everyone was, born by then, if there's any undergrads here. It was certainly a momentous time for us because we astronomers found our first transiting planet. That's a planet that goes in front of the star as seen from the telescope. I'm gonna see if my animation, for some reason that animation's not working. Oh, there it is. Right, so have you all seen a transit light curve or like heard of this? I was saying before that maybe it can't happen in New York City. Well, we can put the pressure on Michael here. But college students,
we saw Venus.
We saw Venus. Amazing. Did you see the phase of Venus? Because you can see Venus's illumination phases like the moon through the telescope.
In the transit of Venus in 2012?
Okay, no, I was thinking of
yeah. But it's hard to see the phases of Venus.
Well, no, it's just a new Venus.
We'll talk about that later. But anyway, all around the country, like literally undergrads can have a project trying to see a transiting planet with like a detector on a small telescope. So they're very common. There's thousands of them we know about, but we got the first one in 1999. I'm going to tell you in my talk like why that's so significant and all the things it's opened up for us. But going a little further back to 1969, there's this really kind of bizarre but weirdly decades later foundational paper by Sapolsky and Solpeter in 1969. And they wrote this paper they called something like Mass Radius Relationships for Cold Spheres of Low Mass. And you can see here, they're actually showing nearness in Neptune and Jupiter and Saturn. And I think what they had done like a couple of years earlier, they worked out an equation of state at very high pressure. Because very high pressure, like inside some astronomical objects like neutron stars or white dwarfs or even part of Jupiter, the pressure gets so high that you can think of the electrons as being pressure ionized. They pop off, allowing the nuclei to squeeze closer together. And they worked out an equation of state in a very sort of asymptotic way. It's called the Thomas Fermi-Dirac equation of state. And they somehow model like a sea of electrons floating around these nuclei. And they came up with a formalism, and I'm just guessing, because who knows what people did. We can never like guess at someone else's motivation, but perhaps they wanted an application. So they made these so-called mass radius plots. And that actually, oddly enough, forms a weird foundation of our field where any new transiting planet discovered now has to get put on the spot. So for my intro, I wanted to just walk you through a time series of this plot, and I'll first explain a little tiny bit about what this plot is about. So what you're seeing here is the radius and Earth radii on the y-axis, and you're seeing, what's this? Got this like old-fashioned pointer.
Yeah, there is a laser pointer as well if you want it.
Sure, you can use laser pointer. Okay, so what you're seeing is, and you're seeing mass in Earth masses, and the first thing you should notice is, wow, just the huge, many orders of magnitude on this scale. A couple of orders of magnitude here, several. And what you're seeing here are in the Solpeter like spirit is curves of constant composition. So these are like fake, they're just models, I'll explain in a moment. But think for a moment about a pure ball of iron. And as it becomes more massive, or as you're imagining different versions of that are more massive, first, as you expect it should grow, is like r cubed, right? Because you know how volume is m over r, mass over density, m over r cubed. But after a while, that doesn't happen. Look at this, look how it flattens out. So that's that electron degeneracy pressure on the inside. As you add more mass, surely it grows on the outside, but on the inside, because these nuclei can squeeze closer together, it actually gets compressed. And it actually does curve over in some cases. Now, these are sort of listed here. They're different planet compositions. They're like a poor person's model, so don't worry too much about everything. I just wanted to walk you through what we found and where we're going. So back in 1999, I love to say I finished my PhD in the last century. And it was so weird because some of my peers, they actually tried hard to finish so they could claim they finished in the last century, 1999. But in 1999, until near the end of it, actually, we didn't have any transiting planets. There were just 0 of them. But we knew this was coming because the geometry tells us that if the stellar axes are oriented like randomly throughout our galaxy, there's going to be like a geometrical argument for the probability to transit. The closer the planet is to the star, the more likely it is to transit. A bad analogy is like throwing darts. If you're right up against the dartboard, it's a lot easier. So these transiting planets, there were like 5 or 6 of, hot Jupiters, there are about 5 or 6 of them. They have a 10% chance to transit. It doesn't mean when you get to 10, there's magically going to be a transit, but it meant we were really close. So knew this was going to happen. Finally got that one. So where do these models come from? Honestly, you could all make your own model if you wanted to. And this sort of poor person's set of model, it's really just 3 equations. Massive spherical shell, hydrostatic equilibrium, where gravity is supported by pressure gradient force. In the atmosphere, that's just like gas pressure. But on the inside, it's like Coulomb forces. And then all the physics is buried in this equation of state, which is how the temperature, pressure, and density are related to each other in equilibrium. And that's a whole field of research I'm not going to talk about, but I showed this little cartoon just to kind of let you know in case you have never heard about like this high pressure research. Have any of you you had a talk or heard about high pressure physics, like super, super high pressures? It's this really small field, and they're really amazing new physics is popping out of it, but they somehow don't get around, and they do need to promote more. I'll recommend one of them to visit you. But anyway, they kind of do lab experiments at these lowish pressures. I mentioned very briefly these asymptotic theories at the very high pressure, but in the middle, there's all kinds of things. There's like quantum mechanical simulations. There's like this huge world of experiments, actually, where they use like these laser guns, or they use incredible facilities. Mostly it's with like beams of lasers all hitting a little tiny sample. And a lot of these actually are really built and used for maintaining our, this is a bit off topic, but for maintaining our nuclear arsenal, because we can't do any tests right now. We're not allowed to test your nuclear weapons. So instead, they have to try to characterize what samples we have remaining and understand the high pressure physics that goes into models that tries to kind of figure out what we have. The planetary or the high pressure geophysicists, they can actually spend some time. That was a sort of long-winded way to say it's really hard to get that equation of state for high pressures. But I had to mention it because it's probably exoplanets' only connection with possibly new physics is that the pressures and temperatures deep inside some of these new worlds can motivate us to study experimental conditions, which might lead to something new. It's not like other astrophysics that can lead us to, I'm just saying this because of the particle physicists, can lead us to like dark matter or dark energy or neutrinos changing. Exoplanets, sometimes we get, it's interesting, but is it physics? So here's my example where we might inspire some new physics. So back to this chart, we have the curves of constant composition, and it's sort of very approximate to say where we find planets on this plot. We can tell you just very briefly what they might be made of. So as the years went by, we got more and more planets. And people really were resistant to this field of exoplanets. They thought it would never materialize kind of beyond just a few planets. People weren't really sure about what to make of this whole field. But as the years went by, we got more and more planets. And these colors are actually the temperature. So we have like an estimated temperature, assuming that the planet and its atmosphere are in equilibrium with the radiation hitting it from the star. We can derive a simple equation and call that the equilibrium temperature. But here you're just seeing, I wanted you to appreciate how many planets we have and this like huge mass radius like look at this. I mean, wow, there are just so many planets on here. The gray ones just have poor uncertainties. I left a lot of planets off that just weren't even, you know, we get a lot of kind of constraints. We'll end here at 2022, but I hope you love this spot as much as I do.
And how far are they from Earth?
These vary from like let's say 10 to 20 light years to 1 or 2,000 light years. So they're only like a small distance towards the bulge of our galaxy. They're not very far. The reason is because it's really hard to make measurements. It's easy to find transiting planets because typically we use all like a broad wavelength spectrum. So we get lots of photons. When we want to try to find the planet mass and put it on this diagram, we have to split the light up into a spectrum of very high resolution in order to do radial velocity measurements, to measure the line of sight motion of the star in the sky. And that's a lot harder. So many of the great exoplanets we found with the Kepler Space Telescope found planets thousands of light years away. We can't measure their mass actually. So here's this picture. I wanted to run a few things by you. Look at all those planets on the top. And I told you how these models, they're just like uniform low temperature. So they're not meant to capture all the physics. It's just to guide your eye. But what's really amazing, if you look at the top here, is that there are some planets that are the same. Well, I've listed the solar system planets are these triangles. So this is Jupiter. There's some planets, it's really shocking, really, that are the same size as Jupiter, but they span an order of magnitude in mass. That's what we were talking about before, that this electron degeneracy pressure on the inside means even though the planet's getting more massive, its size isn't changing on average. Also, look at this. There's some planets that are, even though these models don't capture it, I can tell it to you in words. There's some planets that they're the same mass as Jupiter, but they're much bigger. They're like 1.5, 1.6 times the radius of Jupiter. And this is one of the many exoplanet mysteries that's just kind of on the shelf right now. Because the planets are born big and they contract and cool as they age. But people think they need to have like a huge extra energy source in the interior in order to remain like this puffed out. And there's a lot of theories. So if you were working in exoplanet theory, this might be something you'd work on. Just thinking of the strengths of the skill and the skills of the audience. You try to have ideas of how this energy, like either from phenomenology or from detailed physics codes, to try to, you know, work on the evolution of the planet over time. So that's kind of stuck for now. Let's look a little bit. Let's see. One interesting thing is that this entire diagram is not filled up. I had personally hoped just that we would have some planets that were like massive rocky worlds. But you see, this is a log plot, so it's not fine scale or anything. But on the whole, it's really interesting that we don't have any massive planets without atmospheres. It seems like if a planet becomes a certain mass, it grows in size, meaning it has to have like a kind of low density envelope around it. We have rocky planets down here. These are the ones we're really hoping to study more, and that's partly what my talk will be about. What's very curious, actually, are all the planets in here. You can almost kind of see it on this plot, like this big density of planets that are between Earth and Neptune. That's amazing. No one ever predicted that we would have this sort of huge number of planets in between Earth and Neptune size. And what's so amazing about this is we actually, that's the next, what I'm going to launch into now, is how what appears to be the most common type of planet in our galaxy, we have no solar system counterpart. And for reasons I'll get into, we don't really know what they're composed of. So that concludes my introduction, and I just wanted to pick one example of something on the horizon, because I'm trying to, in this seminar, like bring you up to speed. I don't know of any announcements that are coming, but just, you know, so you know what you should be aware of and looking out for. So I'll tell you about NASA's TESS mission. I'm just kind of curious, because almost all of you are not working exoplanets, if anyone's heard of this. So this is an MIT-led NASA mission. And what it is essentially is 4 glorified telephoto lenses. They're about 10 centimeter diameter aperture. It's like a refractive telescope. Has a camera at the bottom that's 16 megabytes. If you don't work in instrumentation, you probably know what your phone can hold, which is a lot more than 16 megabytes, you know, and your pictures probably can be pretty big files. But oftentimes when these ideas are conceived, you have to go with existing technology. And it still takes 10 years to propose, get it funded, get it built and launched. So it has these 4 cameras, and they're all bolted on a platform. inside this artist's conception of the TESS telescope, it's about this big, like two big washing machines stacked on top of each other, has these solar panels. And this was conceived of to find transiting exoplanets as close as they could be, actually. So not super far away, but tens of light years away. And TESS is like, so, you know, well, you all know about the SDSS. You know, in astronomy, surveys are popular and common. This is like another kind of survey. So it's essentially like a white light, but kind of on the red part of the spectrum survey, monitoring a giant strip of the sky every month, looking for transiting planets. Here's just like a snapshot of a very small part of one of the images. Here is a light curve, a transiting light curve. And I just wanted to briefly share with you how planets are found in this one way from the TESS mission. So on the top left, you see the cameras make out this giant strip of the sky, 24 by 90 degrees. That's so big for astronomy. You know, usually you're looking at a tiny patch of the sky. And if any of you are familiar with the constellation Orion, it fits in just one of those squares. So every month we're measuring, it's like pointing your camera at the sky and taking image after image after image. But in these space projects, our limiting factor is downlink. You know, we can't downlink all our data. That's like, you know, I don't know about you, but when I travel to another country, my phone like throttles. Like supposedly I have a plan for Europe, but it gives me almost no data. It's very frustrating. That's what it's like in this field. Because even if you compress everything, you can still only downlink like 200 gigabytes a month, basically. So what we do is we have computers that do all the work for us. It's like a maturing field over 20 years. I just left you a few details. I'm more than happy to answer questions on it. It's really a whole other talk. We do use some artificial intelligence. We have a lot of different algorithms we've tried. I used to have a leadership role in this mission, and I helped set up some of the software and the team that went through it. But at the end of the day, the MIT team is responsible for selecting the objects that are test objects of interest, that are really prime planet candidates that kind of go out to hundreds of astronomers all around the globe to confirm whether they're planets or false positives or not. So that was honestly like 20 years of work summarized in 1 minute. So that's a lot. But I wanted to get on to talk to you about these so-called sub-Neptune sized planets, because I do think, oops, not sure if that sounds like that was me, but it wasn't me. I just want to say, because to me, this is probably one of the most interesting things going on right now, and the one that we have a chance to resolve with the Webb telescope. So I want you to imagine for a moment a planet made of three different, well, let's say two things for now. Let's imagine that I give you a box, okay? And in this box, I tell you there can be two things in the box. Iron, a lump of iron, and let's say let's say like a helium balloon. So if I give that to you and there's only two things, depending on how heavy or light it is, can you separate out what's in that box? What fraction of helium versus iron is in that box? Yes, actually, you can. Two components and an average. But what if there are three things now? Let's imagine now giving you this helium balloon, chunk of iron, and some water. Well, let's imagine I give you that box and it's so heavy like you can't lift it. You might be able to guess what that is. That would be pure iron. But let's say I give you the box and it floats away. Okay, then it's pure helium. But anything in between, you can't tell what it is if there's three things that average out. And in a nutshell, I want you to take that away with you, because that's our sub-Neptune sized planet. They happen to fall in this range of average density, and we can't tell you what they're made of. And people do really complicated things to tell you, like there's the camp that wants to believe they're all water worlds. This is just only in our heads right now, but we imagine that there's planets like Jupiter's icy moons that are 50% or more water by mass, and they're scaled up versions. So somehow they were born and they may be far away where there's a lot of ices, far from their star, and they migrated inwards, and they have a lot of water ice. That's that middle one, showing you like a rocky core with a lot of water. And this is pretty interesting for a lot of reasons, which I'll get to in a minute. We can also imagine a case like on the right, where you don't have any water, but you have like this rocky core, which unlike Earth, we have a very small, thin atmosphere of nitrogen, but we have like a giant envelope of hydrogen. And those actually come out to the same mass and size. And we can have some in-between cases as well. So this is a problem for us, but I'm only mentioning this because like a large part of the exoplanet atmosphere community imagines that the Webb telescope atmosphere observations of some of these so-called mini Neptunes will resolve this issue for us. Because if it is a water world, it could have like a water vapor atmosphere, which will look very different from a planet with a mostly hydrogen atmosphere. There's a lot of subtleties and caveats why that may or may not actually work out. But we do make it a bit more complicated for ourselves because, and I'm also trying to convey to you that planetary science is just, it's almost like too complicated for our own good. So we have such limited data and too much physics. So here I'm showing you a phase diagram. You must have all seen this at some point in your past. It's showing you pressure and temperature, and this is for water. So, you know, if you had a sample of water at 1,000 degrees Kelvin and at 1 bar, it would be vapor. You can get liquid, obviously, and ice. But, you know, at really high pressures, there's all this high pressure ice, different phases. So some people who, have you heard of this thing, Ice 9? There's this book by Kurt Vonnegut. Some of you who have readers have heard of it. That's kind of wrong. He's talking about
That's good. That's good. It's good. It's wrong, right?
Yeah, because he's talking about our surface pressure and temperature. And if you look at Earth, where's Earth on here? You know, we're around vapor, liquid, and solid. Oh, this is a log scale, so I got that wrong. Yeah, we're far away from Ice 9, Ice 8. See if Ice 9's even on here. That's 7, 8, 10. There is a 9, it's just not here right now, but it's very high pressure, so you don't have to worry about that one. So what we try to do sometimes, because remember, we have a mass and a size, we don't yet have atmosphere measurements, but we don't know what our planet's made of. And it's really hard to talk to the experimentalists in this field because they're like, well, tell us which region of this, you know, very vast plot you want us to measure. And I know that some particle physicists, you can appreciate it, because when I'm the outsider at your talks, you're talking about constraining dark matter, right? So you have this giant parameter space and these blobs where you rule things out. And then they get really mad at us because we show them this. This is what we want. And I'm not going to go through the details for you here. I'm just going to say that models will give you like different temperature pressure structures from like the deep interior to the outside, depending on what your assumptions are. This is one of the themes of my talk, that in exoplanets, we didn't intend for this to happen. We just weren't thinking at the outset that we just have this sort of huge degeneracy in all of the things a planet could be, with limited data to sort through all the options. But there is something interesting about some of these planets because they could get to new phases we're not familiar with. Like some of these you see go through this area that says supercritical. That's supercritical water when it's not quite a gas, not quite a liquid. We do have that somewhere on Earth, by the way, but that's at the deep sea hydrothermal vent. It's like right at the vent. It's so hot at the high pressure at the sea floor. It's a weird phase. It's hard to imagine a planet like that. And one of the challenges we face to understand what's in the atmosphere, I know this is like very like practical and geo-like, but we don't really know how a lot of gases dissolve in water, you know? Like, you know how when you're drinking sparkling water or like soda, that's carbon dioxide that was forced to be dissolved in your liquid. But no one really thinks about supercritical fluid. How does methane and ammonia dissolve in there? And we know some gases are way more soluble than others. Like any planet that has a lot of hydrogen should have ammonia, because nitrogen wants to go with hydrogen and make ammonia. But ammonia is incredibly water soluble. So if one of these mini Neptunes had a water ocean and had no ammonia, we might be able to tell you that, hey, there's no ammonia, there's a lot of other hydrogen dominated gases, and maybe the planet has water, but it gets all complicated because we don't really understand what's going on here. Just to make it even more complicated, and this slide's a bit busy, so you don't have to understand everything on this slide. But do you know how Uranus and Neptune, they're called the ice giants? Well, did you know that we're not sure about that? Because they suffer from that same problem. If you have a mass and a size and little else, you have the atmosphere measurement. You can't really be sure of what's inside. And on the top there, it's just showing you the density. Looks like it's the log density as a function of radius from the inside to the outside, showing you that there's different, different models will fit it. On the bottom left, I don't have time to explain that all, but those are experimental points in temperature and pressure. Gigapascal is a really high pressure. So our Earth, for example, gets to about 300 gigapascal in the center. This goes way further. So there's all different types of materials on the inside. And the US Planetary Sciences Decadal Survey recommended a mission to Uranus as the highest priority for an early 2030s launch. And maybe when we train students in exoplanets, sometimes we also train them in solar system planets, just so they can bring those together and get more info. What people add to the equations, by the way, is from the gravitational moments, like how distorted from a sphere the planet is. You can learn more about the planet when you put that into the system of equations. And the magnetic field is also key, Because remember, for a magnetic field to be generated, you have to have a spinning planet and you have to have a kind of liquid layer. And it turns out that Uranus has a very strange magnetic field. It has like a quadrupolar one, and people think it has a deep layer of like an ionic fluid, and that could be plasma water. So that's kind of where we land. We hope in the future. It seems like from my talk, we're still kind of in the future because we're still trying to work through things. So now we'll get to the third part of my talk, where we are.
Can I ask a question? Sure. What is the field of people who you talk to understand to understand the behavior of this stuff? Who are those people? What are they doing otherwise?
Good question. So it's a bit of a shame it's being recorded because I have to talk a bit of politics now. It turns out exoplanets are so popular, they're unbelievably popular. So a lot of fields want you to work with them so they can get money. And so for
this is uncontroversial so far.
Okay. I just didn't want to say anything bad about other fields and people who are my friends. So I work really hard at the boundaries, usually to find something new and exciting, and other times just to help facilitate this kind of thing. So last summer I was at a conference. Anyone been to a board and research conference? Do they have that in? It's so great. These are conferences where you're sequestered. You're at like a small college or a private boarding school in the summertime, and the whole field is there, and it's very basic. Like you can't say anything that, you're not allowed to bring information outside of the conference, and everyone's always together the whole time. So I went to that conference and I work with them. We have an NSF center, one of the big physics centers, and that's led out of the University of Rochester by someone named Rick Collins. He used to work at one of the big national labs where they do study high pressure physics, what I said at the beginning. So a lot of these people, they're trying to understand the interior of Earth with experiments or theory. They're trying to, just for the sake of pure physics, trying to understand how matter behaves at extremely high pressures that aren't part of our everyday existence. And they do overlap with this high pressure physics community and nuclear physics. So sometimes physics or Earth and planetary scientists more would have that. So you mentioned how I started out at Carnegie. It's now called Carnegie Institute of Science, but it was called Carnegie Institute of Washington. And just so you know how I got to do this was when I arrived there as a staff, there was and is a department of geophysics, although they've now merged, and they have people doing experiments. I don't know if that helped at all. They're usually in geoscience. They're part of Earth and planetary science. Sometimes they're part of a physics department, and they tend to do experiments. You can have your own experiment, diamond anvil cell, where they take diamonds and they squeeze them together. Because remember, pressure is force per area. So you have the tiny area in the diamond and you press them together super, super hard to see what's going on.
But there's no industrial, there's no, there's no application to this.
Well, there was one application. Okay, we're getting really off topic now.
Yeah,
there
sorry.
was an application, I'll just mention it, because it's actually a really big business now, and that's actually artificial diamonds.
I see.
So I have my nice big diamond ring. Because so when you get a real big diamond, it's super expensive. But if you're ever in the market for this, some of you will be. But you in this case, they set it out to grow. And when it gets bigger, it's not necessarily more expensive because the hard part is just getting it to grow to begin with. But what happened was these people doing the diamond anvil, it breaks really easily and it's super expensive for them to do these experiments. So they actually invented ways to make that happen faster, more reliably. And it ended up in a whole other industry now because that a lot of lab-made diamonds. That's not maybe what you were thinking about, but it's there.
Okay.
The reason it's no industry is what industry, when you think about quantum computers or superconducting materials, those are temperature, right? So you could say in industry, we have a reason for wanting to do really low temperatures, just something that you could take away and put in your business or maybe your home one day. But when you think about these super high pressures, there's nothing that really comes to mind, so I don't think really there's any industry for it. It's definitely a really good question. Any other questions about that part of the talk? Okay, so I'm going to move on now to atmospheres. And I set out to tell you about biosignatures and search for life, but I realized it would be more useful to just say where we are. Because now, for the first time ever, we really can think about really finding signs of life by way of gases in an atmosphere that doesn't belong. And that's all because of the new Webb telescope. Some of you saw this already, but in case you didn't, I want to share it with you. I wanted to share with you the way that we find, study exoplanet atmospheres. And actually, before I show this to you, I need to go back to the, I need to explain to you how we find exoplanet atmospheres. So remember when we were talking about this transit light curve, the planet goes in front of the star and the starlight drops by a ratio of the planet to star area. It really happens. There's lots of transiting planets. We know about thousands of them. But now I want to explain to you how we find and study exoplanet atmospheres with the transit method. Well, I want you to think about the planet going in front of the star and being measured at a certain wavelength where the atmosphere is fully transparent. Then the planet's a certain size, you get a certain drop in brightness. Now I want you to think of a wavelength where the atmosphere is very strongly absorbing. All of a sudden the planet's a tiny bit bigger, really tiny bit bigger. Maybe parts per thousand, parts per 10,000, even parts per 100,000 bigger. And we're literally looking at that light curve at different wavelengths to see if it changes in size. And if it changes in size, the planet's a tiny bit bigger. And it means that at that specific wavelength, there's a gas that is strongly absorbing. I want you to just mull that over for a moment. So here you see arguably an incredibly beautiful transit light curve. You're seeing relative flux as a function of time from mid-transit. The transit lasts a few hours. This is a planet called JWST-39b. Data is taken with the Webb telescope. The black is a best fit model. The points are the transit at different wavelengths. It's in micron, and it's showing you, it's running through this loop of data. So what you're supposed to do is look at this figure and try to see for yourself, is there and at what wavelength is the transit deeper than the best fit black line? I just want to make sure everyone sees it, because this is like the heart of the search for life, at least for the next several years. Anyone want to shout out what wavelength you see that? It's really hard to like watch the whole thing at once.
4 microns?
4 point something.
No, some people are more
4.2,
precise than
4.3.
me.
Yeah, but precision's important here. But it's great, right? Like, isn't that awesome? You can see this by eye. This is just wow. So here we are, we have this, but we of course don't show it that way. We're now going to take the maximum drop in brightness per wavelength, or the drop in brightness per wavelength, and plot it that way. So now you're seeing what gets plotted in a paper. Look at this top panel, transit depth in percent as a function of wavelength and micron. These points with error bars are the data that I showed you, but for every transit at every wavelength, it's taking the drop in brightness. So there's sort of this overall 2.15% drop in brightness. You could argue that's the planet itself. And then the wavelength, you said 4.2 something. You can see what the answer is here. Let's see if you can see it, 4.1, 4.2, 4.3. Kind of like 4.4, right? 4.3 to 4.4. That's when the transit depth is deeper. And you can read off here how much deeper it is. And so the points with error bars are the data, and these curves are models. And at the bottom, it's showing you the absorption cross-section of the different molecules. So by eye, you're supposed to try to figure out for yourself, what are the candidates for causing this peak? See this carbon dioxide? That's the main candidate for causing this peak. So this is, just so you know, and to put it in perspective for you, this is like a major triumph for the entire field of exoplanet atmospheres. If you had invited me here 5 or 10 years ago, and I'd shown you what our latest best was, well, let's say when I used to do this 10 years ago, then the audience, well, you would be too polite for this, but the audience would laugh. I'd be like, here's our best thing, we're really excited. But here you can, no one's going to disagree that this is a definite signal. It's so different from a straight line. This is where we're at. So that's kind of what we're doing right now. I wanted to show you well, let me just give you a bit of background about this planet. This is the way we're going to try to find signs of life. We're not doing that right now. This is a giant planet. It's hot, like 1,000 Kelvin. It can't support life. Carbon dioxide is not the dominant form of carbon, but it's a very strong absorber. So that's where we're at here, and yeah. We're sort of reviewing this field, where this field is at now for my visit, and honestly, it's really more chemistry than physics at this point. So I'm not going to bore you with all the details. I'm now going to launch into what we're doing with this data, how we're trying to synthesize it together. But meanwhile, here's the same planet, and it's just showing you a wider wavelength range. It's now taken with a different instrument. And you're supposed to just enjoy all these peaks, these spectral peaks. And you can also look at the colors. Those are what the authors are saying is the identification of these different peaks. So there's carbon dioxide on the far right, and yes, question.
So I guess how much of these peaks are, I guess, known and completely determined by just the chemical structure of these species versus how much is determined by the interactions, the pressure, the atmosphere, and the stuff around there?
Yes, that's a good question. Well, to first order, they are determined by just the cross sections themselves, like just the absorber. And sort of in a clean ideal world, you know, every molecule has a unique set of spectral features, because they all rotate and vibrate and there's different masses on the atom. So that's in first principle. We do have pressure broadening, which does contribute to the atmosphere. It makes it really hard for us because each of these molecules, some of them, they can have hundreds of millions or billions of transitions you have to account for. And to simplify our life computationally, we'd usually ignore all the weak transitions. But it turns out a lot of weak transitions do add up to something significant, and all the tails from pressure broadening end up really mattering. So that's a problem. A bigger problem we have in the atmosphere is kind of less about the temperature and pressure. And this is why I said the details, they may be a bit tedious for like a pure physicist, but photochemistry is really a problem for us. Ultraviolet light from the star hits the planet and causes like a series of reactions. And it's very hard to parse through that. And also sometimes in chemistry, to make it even worse, we have what we call like a catalytic reaction. You can have a molecule that creates a series of reactions that end up with that original molecule being unchanged. And those are very insidious. So it's really the chemistry that changes things more. The temperature and pressure, at least we hope to think that we understand it.
Got it.
But I'm going to be answering that in more detail in the rest of this talk. Anyone want to ask any questions here? So we see water vapor on this planet. That's these new features. We're really just getting started.
I had a question real
Sure.
quick. You gave the example of a box earlier and 3 components in the box. Could we use these data to try and sort of, if you understand one component of the box, the molecules, then you can maybe better understand some of the non-volatile components?
Let me think. Yeah, I haven't heard it. I'm going to think about that one.
Okay.
Yeah. I think what you're saying, I don't know that people have actually thought of it quite that way, and that's a really nice way to think about it. We're so busy. I'm going to tell you why we're not thinking about it like that, because we got so wrapped, this has happened in your field, people get so wrapped up in the standard of the day. And once your computer codes get so big, you're honestly just trying to keep up. So you don't, I don't know if you're laughing because that's true for you, but then you don't have time to think, no one has time to think clearly. So you're suggesting almost like a filter or a tree diagram. I know this, and so hopefully some other things will fall away. Meanwhile, we're trying to solve the whole problem at once.
Well, in the example you gave, you said if you have 2 unknowns, you can figure it out, right? That makes sense.
Right.
And so if we can constrain one of the 3 unknowns, we can maybe better constrain at least the ratio of those.
I love that, and I'm going to have to take that away with me and mull it over. But you're all leading.
I'm gonna keep that actually. No.
Okay. You can keep that. You can keep that. But what I love about you, you're a great audience today. Maybe like the best one in my 3 series, because this is what I'm going to talk about next. How complicated this is. Unfortunately, we're really needing fresh minds to think through this like clearly and in a new way. Remember my other 2 talks, like I'm coming into this field of sulfuric acid. I'm doing new things. I'm thinking clearly. We're too messed up now. We need you to come in and think clearly. So I don't know how many of you have heard of the radiative transfer equation or worked with it. You know, it's a real shame. We do F equals ma. I know everyone here, you have your own equation that you work on, but it's really related to our climate. So there's a sort of thought that at all universities, all undergrads, you know, should learn about this. I'm not going to dwell on it for you. It's just that it is the heart of atmospheres, just how light interacts with, how radiation interacts with matter, and it really sets the stage for everything we do. Just sort of so you have something to like maybe remember in the future, just look at the words I wrote down. Intensity is like a beam of traveling photons, and we're essentially summing up what gets added to the beam and what gets taken away from the beam. And just like when I started out talking about the equation of state, it's all the physics is wrapped up in these absorption cross sections, which I've just called extinction coefficient. Maybe what's a bit easier to parse is, you know, the series of equations we use, and we have a hierarchy of code. You know, in the best case scenario, you write down some little simple semi-analytic model, and then you can have a 1D atmosphere. Then you can go to eventually a full 3-dimensional atmospheric circulation model, which is, you know, the more parameters, the more kind of physics, the more free parameters, the harder it gets here. So we have conservation of, in every layer of our atmosphere, we have conservation of energy, which would be radiative equilibrium or radiative and convective equilibrium. We have energy transport. You know, we have no radiation is created in the atmosphere or destroyed. It's like all passed through, it's conserved. We have hydrostatic equilibrium. I just throw the ideal gas law in. Our pressures and temperatures never get us beyond that. And we have some kind of chemistry, photochemical equilibrium. So in an ideal world, well, the way I wrote it for you to explain it is we have 5 equations and 5 unknowns. We want to know the temperature, pressure, and density as a function of height. We want to know the chemical composition in each layer, and we want to know the radiation in each layer. So like kind of in principle, that should be relatively straightforward. I try to think of it that way. The problem is, you know, our equations are, we do have a lot of problems, and I tried to also just summarize those in words for you because I wanted you to notice. So our first problem, which some of you also share, we have nonlinear physics. So I can't just write down like a giant matrix and invert it. Because it wasn't just 5 equations, it was those 5 equations and 5 unknowns like for every layer. And it was also a function of wavelength. So that kind of made it a bigger dimensional matrix. So that's our first problem, we can't do that. The other thing, which I've already hinted at, we have a lack of input values. So we have, in this kind of problem, we have very poorly defined boundary conditions. And this exacerbates our unquantified physical and chemical processes, which we already touched on, the chemistry, we have cloud formation. And it's hard enough to predict what happens when you know all your inputs and outputs. So that's, I mean, in a nutshell, it would take me a lot longer to unpack all of that, but you can just trust me that it's a mess. And so what we do, which I'm actually guilty of starting, but I think it's got out of hand, and that's where my comment came from, is we live with this. We can't do like a formal inverse problem. So we live with this with what we call retrieval. We calculate posterior probabilities for underlying atmosphere values. So we decide to live with like these, the range of unknowns. So it was like the box with the 3 components, but now we have many components, many components, dozens or more, and we just kind of do that. And so I wanted to just share that with you right now. That's what I wanted to walk through in this next part of my talk. We're definitely going to run out of time, so let me think of how to do that. I think I'll skip over my flow charts and all the details because I just wanted to show you, again, the real example. Why am I talking about loss variability? That is like one of the only exoplanet spectra that's been published by Webb already. And so it's kind of setting the stage for everything else. So I'm showing you again this transit depth versus wavelength. This is our spectrum. The points are data with the Webb telescope. On the far left, they're from Hubble Space Telescope. The details aren't as important to you, but I wanted you to mostly capture our probability, our posterior probability densities, because I wanted you to walk away with like, how well can we tell you? Look, we saw carbon dioxide, we saw water vapor. How well can I tell you how much we have? So if you look at the far left, it's showing you this volume mixing ratio of water. So -4 would mean 1 part in 10,000 water vapor compared to like the average, you know, what's in the atmosphere. So there's very little water, and there's the probability density, and you can see that also for carbon dioxide and a few other gases. But I was kind of curious if you thought this, I'm not gonna ask you to make a judgment call, is this good, is it bad? It is what it is. Despite having great data, you can see that we can't tell you how much there is, right? This is a long scale.
When you say, is there do you have a sense of the what the volume you're looking at actually is? Like, you know, like, so yeah, I guess you must know exactly, you know, like how big this atmosphere is,
yeah,
and how much of the planet you're
like we do, but that's not as relevant. We're think about like a column of air, and we're just sort of averaging over that column, like, so it's the fraction of water.
right.
Yeah.
Yeah, no, it's not important probably for these numbers, but
Yeah.
just in terms of like, is the atmosphere like a tiny fraction of the total planet mass, or is the atmosphere like
Pretty tiny usually,
okay?
very tiny.
Can I ask you something?
Yes.
So, for example, these are the results for one of these exoplanets,
Yeah.
and we expect to get more data for other planets. But do you think these results are surprising, or given that they are all light elements, and we know that heavy elements are formed into stars, and basically we would imagine that the thing that remains is what's from whatever BBN or whatever cosmological process,
Right.
and we must have light elements in tiny things.
Mhm.
Like, do we might be able to say, okay, exoplanets must have hydrogen, must have carbon because they are light and they are way more than other, you know, heavy elements.
That's a good way to think about it. We're not surprised at all. This
Yes.
is exactly what we expect. You know, like the details of how much of this or how much of that, or like we got sulfur dioxide, we weren't expecting that. That is definitely all something. So I'm going to run out of time because I want to leave time for questions, but I now have to sort of rush ahead to tell you about what we're trying to do for exoplanets. So hopefully now you walk away with like what we have. We have a mass and a size, we have an atmosphere, we can find molecules for sure. It's harder for us to tell you how much is there, despite what I tried to briefly convey as an elaborate framework of computational and like applied math sciences. So what we really want to do is search for atmospheres of small planets. And here I'm showing you a real image of our sun and a fake image of a really tiny star, TRAPPIST-1. How many of you have heard of TRAPPIST-1? Has that reached you? This is the most famous system ever. This is a really small star. It's so small, if it was any smaller and colder, it wouldn't be able to sustain fusion in its core. It wouldn't even be a star. And the idea is that, you know, the drop in brightness and the atmosphere being so tiny, the problem is your denominator is your area of the background star. So the idea is that the smaller the star, the better everything works out. And it just works out in more ways as well, because the closer the planet is to the star, depends on the size of the star though, the probability to transit is higher. So an Earth-Sun is out of reach right now. Probability to transit is too low, the atmosphere is too tiny. So our whole fixation is on this. And just for a brief flavor, look at this. This is 23 days of this former Spitzer Space Telescope staring at the star TRAPPIST-1. And a transit, look at all these transits, these are all transits. They're squashed together in time, so you don't see the beautiful curve, but look at that. This was a breathtaking discovery. Also, anyone want to try to guess what this is? There's some rises. Flare, the star is flaring, it's given off some brightness. So this system represents one of our best hopes for the Webb telescope. Here it is now, all the transits separated out and modeled neatly. By Kepler's third law, the further a planet is from the star, the slower it moves. So each sequential transit takes longer. There's a lot of information you can glean from all of this, and it's an incredible system. But these flares are basically a real problem for us. The flares are not just the flares themselves, but these are very active stars. They have spots, and those spots are evolving with time. And so now remember, before our denominator was just pi r squared, star squared. Now it's actually a lot more complicated because it's evolving with time. And the features coming off of that, they're larger than the atmosphere features that we're looking for. And so right at this point in time, like I hope this will go away, but it might not. We're trying to solve this. We're trying to get rid of those features. You know, you can't always just subtract something out. There's several approaches. One is empirical. Other is to do these incredibly detailed simulations from first principles of magnetohydrodynamics and convection, like in a star, to predict what the star spot looks like. We used to think star spots were just cooler stars. So you just make a model and have like your star and then a cool, it's not. They have their own spectral dependency. So that's work that's really ongoing right now. And I do have this, I'm gonna try to wrap up in a moment. You can look at this, don't try to read it. I know you're gonna wanna read every detail here, but I wanted to just capture in a snapshot how the rocky worlds are even more complicated. What this is, it's actually like a clock, so it goes around this way. So it starts out at 1 million years, then 10 million years to the present day. And it's like a review article where Lichtenberg is just capturing like all the different things. You know, the problem with these M-dwarf stars, this might be the last thing that I have time to tell you, is they had like a really, really bad, really, really long teenage phase before they settled into adulthood. So when a star is born, it's just sort of a little weird until it gets stable hydrogen fusion. But M-dwarf stars, unlike sun-like stars, for tens or hundreds of millions of years, they can have so much energy, way more flares, way more activity. So a planet in the habitable zone today, for hundreds of millions of years, it was baked by its star. And so we're questioning whether these TRAPPIST planets have an atmosphere at all. Maybe it lost its atmosphere, and then the material came back out, that was lost over and over again, and they may not have an atmosphere at all. So where are we in our search for signs of life? Well, we can observe atmospheres. We need to know if these small planets transiting small stars, if they have atmospheres at all. Then we're going to ask if these atmospheres have water vapor, because water vapor in the atmosphere of a small rocky planet indicates a liquid water ocean. If all of that pans out, then we're going to try to search for signs of life. We'll need a lot of telescope time, and just like in some other large astronomy projects, you know, astronomers will have to get together and agree to really get that job done. Okay, I'm going to tell you one more thing only because it's going to be relevant soon, and I just have to squeeze this in. It was like a real add-on at the end. I just put it this morning. Well, planets that go in front of the star, if they're on a circular orbit, they will also go behind the star. And we have a lot of astronomy doing that as well. I would feel bad if I didn't tell you something important. So think about, we see the planet and star, we don't spatially separate on the sky. The planet goes behind the star. And if it's a hot planet, in the thermal infrared, we'll see that overall combined light deplete. And we call that like a secondary eclipse. So there are some observations afoot to try to understand whether they have to be these hot, rocky worlds, whether or not they have atmospheres. And one of them was already observed with the Spitzer Space Telescope and shown to not have an atmosphere. It's like, I don't know where things are headed, but I wanted you to know there are other ways to study atmospheres. Well, thank you for listening. I'm going to summarize now, and then we'll have a little bit of time for questions. I talked about the planet composition, how we have these mass radius models to infer bulk composition. We have limited data. It does motivate suites of models and inverse methods, so we at least can tell you what all the range of possibilities are. This is true for atmospheres as well. But one of the takeaways I wanted you to have, because it is maybe expected chemistry, it can still try to solve some big puzzles for us. And one of the biggest ones in my mind is, what are these sub-Neptune-sized planets that we have no solar system counterparts for? Finally, in the search for signs of life, we do have a long way to go. We're still very hopeful. If it's not with the Webb, if it's not with these M-dwarf stars, there are so many ideas, so many plans afoot that will sustain astronomy for decades to come. Thank you so much for your attention.
More questions?
Maybe you mentioned this at the time, but the mass radius plot thing. So how much should I take away from that like Earth is rare because you didn't find a lot, and how much could it be like it's small and it's hard to see Earth-like planets in that sense?
Well, right now you need to take away that Earth is small and we can't find a lot of them. We think these mini Neptunes, the sub-Neptune-sized planets, are the most common type of planet in our galaxy, but we're not sure. It could be that Earth-sized are the most common. So we're not down to Earth yet, but you know what people really like to emphasize is look how they're all along this Earth line. Like that's kind of, at least, I don't know if that means promising or if it means anything, but people do take that seriously. Yes.
Yes.
Go ahead.
Okay, thanks. Yeah, I was just gonna ask about the biosignature. So I like that idea of you find water vapor, then you think there could be an ocean, then you could find CO2. But can you remind us what would be the signature of a bio, or what would be a detection of a biosignature? Is it CO2 with methane, and can Webb actually see both?
Right, good question. What is a biosignature? Everyone has a different opinion on that. People really like the idea of seeing a gas like oxygen and one like methane. And this idea is like from the 1960s. See those two together because those molecules should react and not be there. But you know, on our own Earth, arguably with any telescope we can think of, those two were never present in high enough quantities at the same time. I think it's really all TBD at the moment. Again, the ideas are kind of all over the place. We would like to see two separate gases that shouldn't coexist. But we honestly, at this point, be happy if we could find oxygen or some gas that's really out of equilibrium with its environment.
Yeah, I was gonna sort of add on to your question. I think that sort of like you said, it's observational bias too about finding smaller planets that are maybe further away from our stars, just because like you show the TRAPPIST planets that are really close to their star, you get multiple measurements of the transits, whereas an Earth-like planet probably wouldn't. The probabilities would be too big.
People used to hate these planets around M-dwarf stars for a lot of reasons. They're tidally locked. They rotate one time every time they orbit. They have one side in daytime, one side in nighttime. They think that would prevent. It doesn't. Atmosphere will still, heat will redistribute. People don't like the flares. And the only reason now the pendulum swung to such popularity is because they're all we can study right now.
Any question?
Yeah, so you mentioned that a biosignature could, or something that we're looking for, maybe not necessarily a biosignature, but something that is far out of equilibrium with where we'd expect it to be. But you also mentioned earlier in the talk that these boundary conditions are really, really hard to determine. So how do we know what equilibrium should be? How do we know when we're far away from it?
That's a good question.
Can you just repeat that question just because it didn't get picked up on the mic?
Okay, that was a great question. And that, the question was, I said, I would love to find a gas far out of equilibrium with its environment, and that could be a sign of life. And the really good question is, how do we know what the equilibrium is? Because we have all this going on. That's a good question, and we don't have a good answer. That's a really bit of a cop-out there, but
No, it's fair.
it's definitely tough. But no, that's the good thing. What I love about this field, right? It's gonna go on for a really long time, like so long. You know, and that's why it's great to have you here and younger people, because these questions are ones you might be able to answer in the future. But right now, our data is so limited, we can't.
So is there relevant information about the stars in the data from the transit? Like you said, for example, if you have no atmosphere, then all the fluctuation will come from the sunspots, etc. So the people study that. Is it interesting, or is it just?
That's a good question. Is it interesting? Well, ironically, you know, stars became very out of favor, and people were less interested in them until exoplanets were discovered, and they realized they have to understand stars in order to understand the planet. And yeah, there's some really interesting things going on. One of my colleagues thinks that he can tell you the magnetic field strength of the star based on some transit observations when the planet crosses the limb of the star and the exact shape of that curve. So I definitely think for stellar folks, it's definitely not only revived, but you can also do some almost like a star spot mapping, because if your planet crosses a spot, you can tell something about the spot. So there's definitely a lot going on there.
In a survey like TESS, could you possibly have, say, something that looks like an exoplanet, but it's just like a background eclipsing binary or something like that?
Yes, the question is, in TESS, could you have a transit that's actually a background eclipsing binary star? So a star that's eclipsing itself makes a huge drop in brightness, but if you have an extra star on the same pixel, it washes that out and makes it look like a planet. And that's our single most common false positive.
Sure.
You spoke a lot about the time when a planet goes in front of the star, but there are also fronts. These fronts in the pictures that you show, the front seems to be quite pronounced. Can you extract some more information from fronts of this?
When it first drops.
On first drops, or the back front when it goes
We
back?
can, actually. And there actually is evidence that some of these planets have escaping helium. They have a lot of helium, and they see an asymmetry in the amount of helium being blocked from when it's first going in and one side of the planet shows to when it exits the other side. And they're thinking it's like a tail, that it's like being blown by the star. So far we've been able to pull things like that. People also found, remember I briefly talked about atmospheric retrieval as this inverse computational method? People found a bias in that method where it kept reporting like a much higher temperature than like an equilibrium simplistic calculation temperature. And I found that it has something to do with these hot Jupiters. They're tidally locked. They're being heated really strongly at one point, but very strong winds are pushing that hot spot downwind. And that's an asymmetry they found as well that was looking through all the data. So there are those so far. Like in the far future, maybe it's even better. Maybe we can see, you know, there's a sort of almost a parallel field of our planets sometimes block out a very background distant star. They call it an occultation. And then when it's a point source, like going behind, you literally can map out something about the atmosphere. But I don't know if we can ever do that, if we'll have enough photons.
Yeah, can you talk about there in terms of what Webb can look for transmission spectroscopy? Is it really just the half dozen M dwarfs, or are there?
So there are these half dozen M dwarfs. I have a very strong bias to the search for life and search for other Earths. But there are dozens and dozens of the giant hot planets. There's some mini Neptunes we're trying to sort through. And I failed to convey to you, it's not just transmission spectra, but we have this secondary eclipse thermal emission spectra. Can you believe that for tidally locked planets, they're heated, we see the equivalent of illumination phases, thermal phases, as it's orbiting, like imagine like a crescent to like full. We don't spatially resolve that, but we can map out a temperature difference based on that. So there's like this huge, vast programs of data that we're gonna be getting.
And is there a future telescope that you're most interested in for this field?
There is, and I don't know if you guys have to go. It's getting late. I know we have.
Well,
a
I don't
pizza
think the pizza is guaranteed to arrive until 12:15.
Okay.
So.
Okay, so if you can just wait a second, if I can, because it's really what I want. I wanted to talk about this, but it's, Let me see if I can find it. Maybe you have to see like all my slides. Not sure if I captured it here. Okay, I have to pull it up, but the thing is that, you know, does anyone even want to hazard a guess as to when the Webb telescope was first conceived?
It was in the 90s.
Yeah, around 2000? Before that decadal, right?
I think it was even earlier. I think it was the 90s. So what we're conceiving now, hopefully it won't take that long, you know, but it might.
I think it was supposed to be launched originally in 2006.
2006, yeah. It was a long
I
time
think
ago.
so.
I'm not sure if I'm going to be able to find this. Okay, don't look at my screen, okay? Because I want to try to. I actually did talk about this at one of my other talks, so I'm going to look it up now. How are you organized? I think if that was my public talk. That was the. All right, so in astronomy, it's true, and that there are ideas that come out that can take like a century to get done. In the 1960s, Lyman Spitzer conceived of this incredible idea for a space telescope. And he can seem to have conceived of it along with the Hubble Space Telescope. Maybe he was thinking it would work with Hubble. But the idea is to send a giant specially shaped screen with its own spacecraft to space that would operate with the telescope. And the screen would block out the starlight so we can see planets directly. Then we don't need transiting planets. So we can see any planet of any kind.
To be clear, the screen is very far away from the telescope.
Yeah, we'll get there.
Okay, sorry.
And just sort of for, okay, the question is, why can't we just put up a giant circle? Because we have the area ring pattern. If you block out a point source, light can act like a wave, and it diffracts around the edges. And Spitzer thought about this, actually, and he realized in order to get rid of that diffracted light problem on the top right, he realized you could make an apodized screen. So you go from like fully opaque to transparent, but like very slowly in a very special way. And the brilliant thing he did, because he knew that wasn't buildable, he did some math and he realized you can do a different shape and it actually gives you the same answer as an apodized screen. And he worked this all out mathematically. So that's what we call star shade. It's a giant specially shaped screen that would block out a point source, a star, so it becomes very, very dark. And when my husband, who first heard of this, he's an amateur astronomer, he said, oh, it's like if you drop a pebble in a pond, instead of the pond having ripples, it's very smooth and all the waves are pushed to the outside edges. So I like to say it that way, and that's what the bottom one is showing you. You're not making the light go away, you're just making it diffract in a different pattern. So we have this really nice animation made by NASA showing you one idea of a telescope and starshade launching together. When the starshade deploys from its stowed position, and this inner truss expands and the petals kind of snap out and lock into place. This starshade would be tens of meters in diameter, and it would formation fly tens of thousands of kilometers from the telescope. And in this image, this animation, it conveniently reveals an Earth and a Jupiter. This is a real project, it's been going on. I was trying to say that Spitzer first thought of it in the 1960s, and every decade it got revived. There's a French optical physicist 10 or 20 years later who did more math and worked it out even more detail. It had been revived once it was called BOSS, Big Occultable Steerable Satellite. I got to lead a team starting in 2013 to bring it back again. And just in this case, just for like another little political story, NASA was reviving this idea of how to find planets from space. And they made Starshade, they made another one that has a starshade, if you will, a chronograph on the inside. And word had it that they started the Starshade version to kill it. Because, you know, if you can demonstrate it doesn't work, it's actually a good thing because it removes a complicated option that you'd otherwise have to keep funding. We actually showed that it was possible. Here's a petal prototype that was built at JPL to show that it's actually doable. There's lots of scale model engineering going on. The heritage comes from large radio deployables, that central truss that folds up and expands. And this is really a very compelling and interesting way to try to find other Earths. That's my favorite future telescope idea.
Awesome.
And once you point it to a star, I mean, it's going to be pointing at that star, or you cannot, I guess, reuse it for another star.
You can reuse it.
You can,
and that's the limiting factor. And so when we think about this, there's the traveling salesman problem. You have to figure out what's your most efficient way to move across the sky. how long do you want to wait on one star? You know, if you don't see the Earth, does it mean it's not there, or is it just conveniently hidden and you've got to wait for it to come back out? And when you think of star shade and the engineering constraints, it could typically have 60, like moves. So you've got to kind of map it out that way. You know, everything NASA does now, they want it to be refuelable, serviceable. So then you could kind of keep going maybe. Their star shade has a lot of different versions, a lot of different sizes. I can go into sales mode very easily. A lot of sizes, a lot of versions. Get the job done.
Let's thank Sara again. And there will be pizza in 802, I'm told. That's a floor down there. Thank you.
Thanks, everyone. Thanks for all your great questions and interaction today.
Thank you.
Where are you?
Yeah.
Just all right.
Thank you so much.